The washer method and the shell method are powerful results for finding the volumes of solids of revolution. And by making slight modifications to these formulas, we can find volumes of solids of revolution resulting from revolving a region R in the xy plane about a vertical line other than the y-axis, or about a horizontal line other than the x-axis. We will work through an example to illustrate one such scenario. But before we do this, let's review the shell method and the washer method. Suppose that we have a region R that's bounded between the curves y equal f of x and y equal g of x from x equal a to x equal b. If we take this region and revolve it about the y-axis, we obtain the following solid of revolution with a hole in its center. For a given value of x in between a and b, if we take the corresponding line segment extending from the curve g of x to the curve f of x, and revolve this line segment about the y-axis, we obtain the surface of a cylindrical shell. The height of this shell, which is given in the three-dimensional image here and in the two-dimensional figure here, is equal to f of x minus g of x, and the radius of this shell is equal to the value of x. And recall that the shell method says that the volume of the solid is equal to the integral from a to b of 2 pi x times f of x minus g of x, where x is the shell radius and f of x minus g of x is the shell height. But keep in mind, if we revolve a region R about another vertical line besides the y-axis, the shell radius and the shell height formulas may need to be revised. Therefore, we will need to modify the formula if we revolve R about another vertical line. Now recall the washer method about the y-axis. Suppose that we have a region R bounded between the curves x equal q of y and x equal p of y, and suppose we revolve this region about the y-axis. Then we obtain the following solid that's bounded between this outer surface and this inner surface. For any value of y in between x equal a and x equal b, let's draw a line segment from q of y to p of y. If we revolve this line segment about the y-axis, we obtain the surface of a washer given here. And recall that the washer method says that volume is equal to the integral from a to b of pi times p of y squared minus q of y squared. The value of p of y is the radius of the outer circular boundary of the washer, which is the distance from here to here, or seen on our two-dimensional graph, it's the distance from here to here. We will refer to p of y as the outer radius. So in the first part of the formula, we have the outer radius squared. The value of q of y, on the other hand, is the radius of the inner hole of the washer, which is the distance from here to here, which is q of y. So q of y squared is the inner radius squared. And once again, we will need to modify this formula if we revolve R about another vertical line besides the y-axis. To illustrate how we can modify the washer method and the shell method in cases where we revolve a region R about a vertical line other than the y-axis, let's work through the following example. Let R be the region bounded in the first quadrant by the curve y equal 1 minus the square root of x, the x-axis and the y-axis. Determine the volume of the solid generated when R is revolved about the line x equal negative 1/4. Here's a graph of the region R that's bounded by the x-axis, the y-axis, and the curve y equal 1 minus square root of x. And suppose we revolve this region about the vertical line x equal negative 1/4. When we do this, we obtain the following solid that's bounded in between this surface and the inner cylinder. For a given value of x in between x equals 0 and x equal 1, we draw a vertical line segment from the x-axis to the curve y equal 1 minus square root of x, which represents the height of the corresponding cylindrical shell in the three-dimensional solid. Using the shell method, the volume is equal to the integral from 0 to 1 of 2 pi times the shell radius times the shell height. In this case, the shell radius is equal to the distance of the value of x from -1/4. To obtain the distance between 2 points on the number line, we subtract the left point from the right point. So we have x minus a -1/4, which is x plus 1/4. Now recall that the shell height is equal to the length of this line segment, which is simply 1 minus the square root of x. Therefore, volume is equal to the integral from 0 to 1 of 2 pi times x plus 1/4 times 1 minus the square root of x. If we move the constant 2 pi outside the integral and expand the remaining terms, we have 2 pi times the integral from 0 to 1 of x minus x to the 3/2 minus 1/4 x to the 1/2 plus 1/4. An antiderivative of this integrand is 1/2 x squared minus 2/5 x to the 5/2 minus 1/6 x to the 3/2 plus 1/4 x. Evaluating this expression, we obtain 2 pi times 11 over 60, and this simplifies to 11 pi over 30. So the volume of the solid is 11 pi over 30. Now let's go back and confirm this result by finding the volume of the solid using the washer method. So once again, we are taking the region R and revolving it about the line x equal -1/4. And using the washer method, we pick a value of y in between y equals 0 and y equal 1, and we draw a horizontal line segment through the region R. Revolving this line segment about the line x equal -1/4 gives us this surface of a washer. So in this case, the washer method tells us that volume is equal to the integral from 0 to 1 of pi times the outer radius squared minus the inner radius squared. To find the outer and inner radius, we must first solve this equation for x, and you could verify that x equals 1 minus y squared. In this case, the outer radius, which is the radius of the outer circle on the washer, is equal to the horizontal distance from the line x equal -1/4 to the curve x equal 1 minus y squared. And this equals 1 minus y squared minus a -1/4, or 1 minus y squared plus 1/4. So the outer radius squared is 1 minus y squared plus 1/4 squared. The inner radius is the radius of the inner circle on the washer, which is equal to the distance from the line x equal -1/4 to the y-axis, which is a distance of 1/4. So we have minus 1/4 squared, or 1/16. Therefore, by the washer method, we have found that the volume is equal to the integral from 0 to 1 of pi times the quantity 1 minus y squared plus 1/4 squared minus 1/4 squared. Placing pi outside the integral and expanding the remaining terms, you could verify that we obtain pi times the integral from 0 to 1 of y to the 4th minus 4y cubed plus 13/2 y squared minus 5y plus 3/2. An antiderivative of the integrand is 1/5 y to the 5th minus y to the 4th plus 13/6 y cubed minus 5/2 y squared plus 3/2 y. And evaluating this expression and simplifying, we obtain 11 pi over 30, which equals the value we obtained using the shell method. Now typically either the washer method or the shell method will be easier to apply. In this case, the calculations for finding the volume using the washer method are slightly more involved than the calculations used in the shell method. In this case, the shell method is easier to apply than the washer method.